Okay. Uh, Hi everyone. So this video we will continue our lesson from the problem of heteroskedasticity. So from our previous stop, I did mention that the condition of making OLS blue, which is based in the unweighted estimation, is that the assumption 5 we need to have the data of Homo skedasticity, which is the variant of the error term condition of x must equal to the constant term sigma. So if this is not in the condition this way, we will call it heteroskedasticity. So basically, what heteroskedasticity is that, so from this example, we have the regression of wage to the education. And as we see that when the number of education years increase, the distribution of the weight is expanding. So this means that the variance of the residue or the error term in this case, it's increasing. It keep increasing when the education year is increasing. So this is the size of heteroskedasticity. And if we face this problem, then the variant of the regression, which is mean the standard error that we have, and also the t-test, is um, it's biased. So we cannot use the normal standard error and the t-test. So how can we detect it? Okay, last time we mentioned that we can test by the Bruce and Tekken test, and we can do the Y test this way. And from the comma, after you regress, then you put IM test and then Y, and then this is the test for homoskedasticity for null hypothesis and alternative hypothesis. We have that unrestricted heteroskedasticity. So this is statistically significant, which means we reject the none. So the data is unrestricted heteroskedasticity. So if we have this problem, so how can we deal with this? So the first thing is we can adjust the standard error because heteroskedasticity is a problem with a standard error. So we can adjust the standard error to be heteroskedasticity robust standard error. So this is the step. So the first step, we regress and we obtain the residual. The second step, we regress the independent variable and we obtain the residual from this sub-equation, and also we obtain the SSR from these two equations. After that, we will compute the variance of the beta 1 and beta 2 using the residual from the sub-equation and also the residual from the main equation divided by the SSR. After we get square root of this, we will get the heteroskedasticity robust standard error. In this data, you can directly use the command. So after regress, you put the comma and then type robust. So this result, it's dealing with the robust, dealing with the heteroskedasticity by using robust standard error. So you can just use this result to integrate directly. Okay. So other than using robust standard error, we can we can erase the problem by using with least square. So basically, we need some way to divide all variable. Then we can cut out the problem of heteroskedasticity. But how can we get the weight? We will use the what is called generalized least square to compute the weights, and what is actually in practice is the feasible generalized least square or FGLS. In this, we have the 5 steps. So the first one, we regress the main equation and then obtain the residual. After that, we put the residual square into the logarithm form, And then the third step, we regress the logarithm of the residual square to the all independent variables again, and then obtain the fitted variable g hat. After that, we compute the g hat and then regress to the all independent variables again. After that, we exponential the fitted value and obtain the h hat. At the end, we regress the all independent variable again in the main regression, divide by square root of the h hat. So after this, the result will be called FGLS, feasible generalized square. Okay. So the good part is that FGLS is usually more efficient, which is smaller variant than OLS. However, because we manipulate the data, so it's not unbiased anymore. So the result may change from what consistent term is. So it just balance, or if we use the robust standard error, you will get the consistency, but if you use FGLS, you will get the efficiency. So it depends on the assumption. Basically, the robust standard error is more popular because you can keep the consistency term. Okay, this is the manual that you can do FGLS. And another technique that we like to use to solve the heteroskedasticity, which is not actually to deal with the problem, but to scale down the data itself, so, or the variant of the data itself, is by using logarithm. So if we use log to variable, usually the size of standard error will be small, so it's more likely to be consistent, or the variant of the error is more likely to equal to constant. For example, so I use the logarithm of the weight variable, and as you see from here, it's just between -1 to maybe 3 point something. So the data is not moving a lot. So after that, we use this logarithm weight to regress by education, and then use the Bruce Bakken test and use the white test. You will see that both of tests now, it's statistically insignificant, which means we don't have the heteroskedasticity. Our data telling that now we have only homoskedasticity. So if this something is like this, then you don't need to worry about the heteroskedasticity anymore. You just use log and then just go ahead with interpret that. So this is all we have for this problem. So after you use ULS, you use Bruce Bacon or white. If it's homo, then OLS is fine. And then after that, if you get hetero, say you can go with logarithm, and if log is produce the result of homo, then OLS is okay. But if it's not, if the logarithm is hetero, then you go back again into pick two option, which is robust standard error or the FGLS. Okay, so that's it for this chapter. Thank you.